Hi everyone, welcome to a new video. We're gonna be going through everything you need to know about neural networks as a first introduction. We're not gonna be coding anything, we're not gonna be doing any math at all. It's gonna be quite simple and just gonna give some insights that you need to know in order to understand how neural networks work. Basically, we're not gonna cover the whole training process. We're not gonna cover a lot of details. What I'm gonna just explain is give you an introduction on how you can start using neural networks from the playground.tensorflow.org. This is something open source by Google. It's quite old, to be honest. I started learning neural networks like in 2019 or so. 2018, I was doing some things with MATLAB. But basically, my introduction to TensorFlow was 2019, Keras and all that kind of stuff. So that is where I started learning about these things like around 4 years ago. So yeah, basically today we're gonna cover everything you need to know to start playing with this, everything you need to know to understand how these things work on a high level point of view, and understand which are the challenges that we have nowadays. Because nowadays we have a lot of types of neural networks. The transformer is quite famous, but there was a lot of things before transformers, and there's a lot of people trying to get into the field. They just try to go through transformers first thing. That's something I would highly not recommend anyone. um, Not even partially, like, don't start from there. Start from the basics, try to get an insight, try to get into the thing slowly, but do it in a way that you're gonna gain a lot of track, a lot of background, and just as soon as you get more comfortable with the topics, more comfortable with the things that you're working with, that's the moment you have to tell yourself, hey, let's go through the big thing, let's try to understand how LLMs work, how the transformer works, which are the different things that you need to consider when you fine tune a model, all that kind of stuff. So let's get into it. Let's start from the beginning, something basic. What you're looking at right now, as I said, is a playground TensorFlow. This is a place you can go. This is open source if you want to deploy it in your machine. I'm just using the web page that they give, just basically because it's quite faster, to start playing with this. As it says, don't worry, you can break it. It's gonna work. We're gonna play with a lot of different things. So first of all, what is a neural network? What you're looking at right there is basically a neural network, right? So what we have is it's an algorithmic entity, and I want to call it entity because it is both a data set and both an algorithm. It is a data set because what is encoded in the neurons that you are looking at right here, that they have different colors, is basically part of the data set, and it's also algorithmic how it works. Like, you can change these values in a way, and that way is an algorithm called backpropagation. There are other methods on doing that, but this is basically how we modify, how we train, how we change the values, how we transfer a model that has been trained on a certain data set into another task. That is basically it. It's an algorithmic entity, right? This algorithmic entity that is a neural network is trained giving certain kinds of data. Like, we're gonna throw it data and we're gonna tell it, hey, this kind of data is of this type. Or we're gonna tell it, hey, this is some past data. This is the next data that should come up, right? These are the two main things that we are using neural networks for. We're using them either to predict the next value, which is basically LLMs. It was used before on the stock market to predict which is the next expected value for a certain asset. It's been used for weather analytics, like which is the expected temperature on the next year, the next month, the next, giving this prior data. It's been trained on basically those things, like which kind of type is this? This image is a dog, this image is a cat, this image contains a bottle of water or not, or whatever you're training this with. And the other thing is which is going to be the next predicted token, which is going to be the next predicted value. So basically those kind of words are either classification or regression, and that's basically it. That's basically neural networks. That's basically what you can train your neural network for. Let's imagine, for example, the case of stable diffusion. You generate images, right? So what is basically the image generation process? It's predicting which is the color, which is the value for each of the pixels on the image, right? So we are just predicting or classifying things. That's basically what we do, right? So that's the first thing, what we're gonna be doing. The second thing is data. Data is just basically a bunch of data points. It could be an image, it could be a text, it could be a value, whatever you have ready. So we have different kinds of values in here that we can choose. So let's start with this one because this one is quite easy, right? So neural networks have been historically great algorithms, great entities that you can use in order to create a model of your reality. This is our reality. This is the data. So what we're gonna do is we're gonna train these values in here, right, in order to make a better model of the reality. This is the output that we have right now, right? So all the different dots, color on different colors, they are the reality. And what we see on a more, you know, a less pronounced color, let's say, right? This is more light colors on the background. What we see on this kind of square are the predictions, right? So the neural network right now is not trained, right? It's not trained because it's predicting these values in here, which are blue, and we see that the reality is that it should be orange. And on the other side, we're seeing a lot of orange right here, which we see a lot of dots that are blue. So basically, all these dots in here should be on a background that is blue. All these dots in here, right, that I'm just circling, should be on a background that is orange. And basically, everything should change to adapt to the reality. But if we change the reality, this should change as well, right? As we can see, this is not trained. And even though we give different data, the values inside the neurons are the same for each of the different distributions. So we need to change something, right? We need to change something. I'm gonna start with this one in here. So the neural network, as it's called, it's a network of neurons, right? It's a network of neurons, so we need neurons. So what is a neuron? A neuron is basically each of these squares. It's basically a value that is inside, let's say, a container. So for each of the inputs that we're gonna give, this neuron, as in your brain, because this is basically kind of a metaphor for your brain or any other animal's brain, is going to be activated or not. Like, I'm gonna give you a 13 data and it's gonna be activated or not. Each of its neurons is gonna happen that, right? So for each of the input, each of the neurons is gonna react differently, right? It's gonna say, okay, you're telling me this part is orange, this part is blue, right? This is my model at the moment. Like, this part is blue and this other is orange. And for each of the neurons is gonna create part of the model, right? No single neuron is gonna be enough to create the reality model. So we need all the neurons working together in order to create that reality model. Otherwise, it's gonna be pretty much impossible. So we need a network. We need a lot of neurons to interact with each other, right? We're gonna give a lot of data. We're gonna train them for that data, and the neurons are gonna start learning different things from the data. And the more data we give them, the more things they're gonna learn. And there's gonna be a point in which if we give a lot of data and the data is so different from each other, the neurons are not gonna be able to learn all those things. So we're gonna need more neurons. This is basically how it works in the deep learning ecosystem, right? So it's called deep learning because the neural networks are gonna become deep. They're gonna have a lot of layers, right? So each of these things in here, this is a layer, right? And this is another layer, and this is basically the output, and this is the input that we give them, right? So for each of the inputs that we give them, these neurons are gonna have, are gonna react differently. Also, we have two kinds of processes in a neural network. Either we are training the neural network or we are using the neural network. If we use the neural network, the neurons are not going to change. They're going to have the value that they had after the training process. If we train the neural network, all those neurons are going to change. All those neurons are going to evolve depending on the kinds of data that we give them. So it's important to understand that, because if we are using the neural network for training, we are going to evaluate different things as if we are using the neural network for inference or the day-to-day use, right? The day-to-day use would be, hey, neural network, is there a cat in this picture? And the training usage of it is going to be, this is a cat on a picture, right? Learn the features that it contains so that we can predict with other kinds of cats or the cat on other positions, and we can predict all those kind of things. So this is basically a neural network. And we have these two neurons here in the output. So the planning here is we're telling the neuron, hey, what do you think is on this 13 point? Is it blue? Should it blue? Should it be blue? Should it be orange? And of course, as we can see, this is not 100% exact, right? So if we try to train, we can give it a plane here, and we're gonna train on this data that we're inputting here, this circle and this donut, this orange donut, and we're gonna see what happens. We can make the data more complicated, right? More complicated. We can, kind of shuffle the data. We're gonna just keep it easy, just no noise by now, then we're gonna just make it more complicated. Look at how complicated this is. It's important that the data that we introduce to the neural network doesn't have noise in real life, because if it has noise, it's going to be difficult for it to learn. It's going to learn the noise, right? That's one of the biggest problems that we have nowadays with neural networks. They need to be the noise, all the data that we give them. And then we're going to use this batch size. I'm going to explain it quicker later, because we can tell the neural network here, can you learn from each single piece of data that I give you? Or we can tell the neural network, hey, here is a batch of data. Here is a package of data. Can you learn from the package of data? So depending on how big is this package of data, the neural network is going to train things at a certain point, right? At each iteration of the training process, more slowly or less. Think about it. Like, imagine that you are trying to learn something. You can try to learn how to sum numbers one at a time, like you do one calculation, then you do another calculation, or you can learn how to sum numbers giving you a batch. These things work differently. Like, we're better at trying to learn from each, right? But neural networks are better at trying to learn from a batch of data. Like, it's like when you study about something. You read the text, but you don't memorize each word. You should memorize each word. You should read a paragraph, try to understand the paragraph. So the same goes in here. We're gonna just give it a paragraph of data. We're gonna give it a batch of data, and it's gonna learn the things that happen in there. If we give a lot of information on the same batch of data, what's gonna happen is it could get confused, right? If we give too little information, it's gonna be hard for it to learn new things. It's gonna take more time, and it's not gonna generalize. It's not gonna learn anything. So giving a batch size in between is gonna be the key in here, right? So this is basically it. And we can give more data from one kind, more data from another kind, or something more, balanced, more points or less data points. So we're gonna train on 50% data points in here, right? Well, here's a little explanation of the things we're gonna be doing, but basically this is basically it. And then we have all the things in here. We're not gonna touch them by now. We're gonna touch them later. I just want to understand how this process is gonna work. But there's gonna be a lot of things to kind of change, fine tune, and see how the thing works, right? So, as it says, the training process is iterative. It's gonna be learning on epochs, right? I'm not just giving you how this training process is gonna go, but it's gonna learn on epochs. It's gonna be one epoch that's gonna be learning about something. The next epoch is gonna take what he has previously learned, and he's gonna try to learn more things. The next epoch, the third epoch, is gonna learn from what he knows and something more, right? So at each epoch, we're gonna be modifying the values of the neurons depending on the kinds of data that it sees at each point, right? And then we're gonna have this loss. This is how we're gonna evaluate the neural network. How we know the neural network is doing right. Right now, it's pretty much being random, right? So we're gonna focus on the test loss. It's kind of being random because as you can see, these blue dots in here should be orange. This, all that kind of stuff. This orange should be blue. This blue right here should be orange. Pretty much it's a 50-50, right? So we are looking forward reducing this loss, right? You reduce the loss, and as a side effect, your accuracy, your performance of the model is going to improve. I'm not going to give a lot of terms in here because we're just getting started. But yeah, that's basically how it's going to work. So if we go for a play, as you can see, the loss has been reduced. We have run 53 epochs, okay? And it has learned a lot of things. It has learned that all the dots, the blue dots in here should be blue, and all the things happening in the orange should be orange, right? So it has learned how to identify all those different parameters. If you closely look at it, the values in here in each of the neurons has changed during the training process. Mainly the thing has happened in here, in the output. So we have improved a lot. We have a loss of 0.034 right now. And it's very important that if we click to go on forever, it's very likely that it's going to go through test loss 0. Yeah, at the end. So we're going to stop on here. Right, we're going to stop on 503 epochs, sorry. This is basically our trained model, but there's a little catch. If we change the data, it will fail. Like let's train it again. It goes so quickly, right? Let's train it again. Right, we have trained, but if we increase the noise, the model is not gonna be capable of knowing that new data. Let's stop in here. So what is happening in here? We have stopped on epoch 112, and we are seeing a loss of 0.2. Like this is not looking like what it should. Like before it has worked perfectly well, straightforward. Why doesn't it work the same? Always. That's a question that we need to ask ourselves. And the main thing is this kind of thing is stochastic, right? It's probabilistic. It's gonna be doing changes on the different neurons depending on how much each value on the neuron affects the wall value on the result. So we're not gonna get the same result all the time, right? It depends on how the neurons are initialized. It depends on which kind of strategy we follow. So it's gonna change, right? So at this kind of step, we're seeing that this is not going anywhere. This has just chosen to choose all these values in here that should be orange right here, and all this here that should be kind of orange. The model is not identifying them correctly, right? And it's just generating this thing kind of wrong. So with more time, it's very likely that we are gonna get into the model that we saw before that was capable of identifying the blue dots as blue and the orange blue dots as orange. Like all these regions should be orange, and this little zone in the middle should be blue. Depending on how the distribution goes, it's gonna be harder for a neural network or more, kind of easier. So what is happening in here, how the training process is gonna go, is we are gonna have a function, right? We're gonna have a function depending on all these values. We're gonna have a function, and we are looking forward reducing the loss. We're reducing the loss on the neural network. So we are descending the gradient. This is something that's called, right? Gradient descent. Maybe you have heard about it on the neural network ecosystem. And what basically happens is we are gonna evaluate how the different parameters, how the different neurons in the neural network influence the prediction, right? So if a neuron that influences the prediction a lot is kind of giving the wrong choice, there should be a mechanism to update the neuron's value to something different so that it doesn't affect the result, right? We're just trying to make sure that the neurons are giving an output that when considering the whole network, the output is correct, or the output follows the kind of distribution that we gave it. It's going to be correct or not depending on how the distribution of the data is, right? So is it good a model that we train for a lot of epochs and a lot of iterations and basically has a loss of 0? Well, yes and no. Well, yes, because, well, we have a model that predicts its single point as it should, but no, because what happens with the data that is not in the distribution, right? We are gonna take our data, we are gonna split that data into a distribution that we're gonna be using for testing once the model is trained, and another distribution that we're gonna be using for training, right? Like, we're gonna train the data with half of the points, we're gonna see how it evolves, how it improves, all that kind of stuff, and once we have it trained, we're gonna check with the other half of the data how the training went through. And it's very likely that it's gonna be, if the model is so precise on a certain data set, it's not gonna be able to be precise on a data set that is not 100% exactly. That's what we call overfitting. And what happens with a model like this, that it's not learning, right? It's, if you just look at this region right here that I'm just pointing, right, on the top, it should be orange and it's being blue. It's not learning, it's being on an underfit. So we need to keep training the neural network for sure. Right? Let's go for another epoch. We can go one epoch at a time if we just click on this button. Okay, we're gonna see the evolution. But if we click on play, we're gonna be seeing how this at some point around 500 epoch as before, we get the result as we expect, right? And this model is pretty good, but it's very likely that if this is our training data set and then we have some data that is kind of noisy, this is not gonna behave as it should. So it's kind of good to have a kind of 0.9 of accuracy or some kind of loss. As soon as you have a bit of loss, that bit of loss is meaning that, hey, there's room for improvement of your neural network. There's room for bringing data out of the distribution so that it learns those values. Because if the model is 100%, it's gonna be 100% for those points. But as soon as you bring data that is slightly different, it's not gonna work, right? So we need to avoid overfitting. We need to kind of train, but we don't need to. It needs to learn. It needs to have that uncertainty on certain data, right? So it took 500 epochs. Your challenge right now is, let's try to train these on less epochs, because it has taken around 500 as before. So how do we train on less epochs? How can we make this model more performing on less training steps? By just basically adding more layers, right? That's how it works. So we have 2 hidden layers at the moment. Let's add another layer by clicking in here, and let's make it a bit bigger, like 4 neurons in both, right? And then let's make an output of 2 neurons. Let's go for it. On 100 epochs, we have it trained. Wow. So just by adding 1 layer, and I don't know if on even less, let's go slowly. On 84 epochs, we have it pretty much trained. This would be, in my opinion, the best model that we have come up with. It has 0.5 to 4, and it has some uncertainty in 13 places. You know, the distribution is not so fitted on each of the dots. Like, if running for a lot of epochs, what's going to happen is it's very likely that for each of the dots, it's going to identify them as something different. Well, that's pretty much what's going on in here, right? So, can we go down 84 epochs? Let's try with another layer. And as you can see, you can add layers, you can put more neurons on one of the layers, less neurons on another of the layers. Let's bring more neurons, like let's put in here some big compute guys, like 21 neurons, and then here let's go for 5. Okay, let's see what happens. 17 epochs, and look at the model that we got, right? So as we're seeing, adding more layers, adding more neurons is gonna make the model to train faster. That's how it works. This kind of distribution is quite easy because it's just a circle in the middle and then just a donut around it. But let's try to get something harder, like this spiral. Let's see what it takes. It's gonna be harder for it, you know. It's gonna be harder. It's gonna try to learn the different, you know, sections. It's gonna take much longer, and it's gonna have these kind of vibrations. Those kind of vibrations are very common in language models nowadays. These kind of vibrations are the way we are training the neural network. Is we are just asking for a reduction, a continuous reduction in the loss. So what's happening in here is we are reducing the gradient down a slope. Basically, just imagine the loss function as if it were a slope, right? And we're looking forward the values that make that point of loss go down the hill, go down the loss, and make the loss close to zero. As you can see, this is the model that it comes up with, right? We could keep training for longer, but it's not gonna be improving. Even as we can see, it's likely that the loss is gonna increase. That's something that happens. If you keep training on the same kind of data, it's very likely that in the future, the model is gonna start performing worse. And that happens, right? But let's stop in there. What we saw is basically we are just modifying the values on the different neurons. Basically, modifying the neurons means the values that or the features that it learns from the data set are different. And what we're trying to do within here is basically trying to find out a way for that loss to go down. But what happens? This spiral is complicated. I told you guys, this is kind of the hardest that we can have on this data set, and that's why I brought up the next, because I'm just looking forward giving a straightforward explanation on what's going on, the main topics about it, and afterwards we're gonna have more videos on this, but I just wanna lay down the foundations. So what is happening in here is it is unable to learn this distribution. We have a lot of noise. We are seeing a lot of noise. We are seeing a lot of spikes. Why do we have those spikes? Those spikes on the loss happen because when we are descending the gradient, we are finding a direction. We are finding which are the steps to take. And basically the steps to take are changes on the neurons, right? If we change neuron number 1, X number of values, right? X number of units, or increase it, well, what we're doing is telling the loss to go in a certain direction in that slope of loss, right? Let's look at an example on Google. um, this is what is happening, right? This is kind of the loss function. What basically happens here, we're just trying to descend the gradient for a loss, right? Like if we are higher, that means that the loss is higher, and we don't want that. We want to move along the loss, right? So that we get down to the best position, and the best position would be to have this thing look like a spiral and nothing like this kind of gibberish that happened at the end, right? Because it was just trembling a lot, didn't look like it, right? So that's what we're trying to do. But what happens if we are trying to get down the hill right here? Well, let's get this one right here. We're gonna end up on a local minima. That's called a local minima. That's not a global minima. We're looking for a global minima. We're looking for the point in which the loss is the least, is the smallest loss possible. And that's not the case in here, because in this case we have found a local minima. And once we are in this local minima, it's very hard to leave, because the algorithm is just trying to improve on that area, but it's not gonna find something, because this kind of thing in here is kind of, going up a bit. So it's gonna be hard. We need to tell the algorithm, hey, it's okay to go up at some occasions if you find a better result later on. But this is basically what's happening. So this trembling that we found on the loss function basically means it has a lot of points, it has a lot of ups and downs, it's making the model that don't know what's going on, like in this one right here. It's kind of, it tries to go in a direction which feels like it's gonna be better because we are descending the gradient, but then we find, when we try to go even lower, we are just getting into places in which it is higher. So that's gonna go wrong, absolutely wrong, right? So that's something we need to take care for, right? So what can we do? Something we can do is try to change the activation function. So the TAN-H, the TAN is not the best one nowadays. It's gonna generate a lot of trembles. The sigmoid as well is gonna generate a lot of trembles. The linear is not gonna bring any non-linearity. We're looking for non-linear function, so we're gonna choose ReLU, which is the state of the art in many use cases nowadays. We're gonna try to reduce a bit the learning rate because 0.3 is quite high. 0.03 means on each step, for each of the changes that you are expecting your for each of the gradients of your parameters, change that parameter on a value by the learning rate. So it's basically telling if the gradient of each of the neurons, basically the gradient is how much each neuron affects the generation of a 13 outputs. If the gradient of each neuron is 1, I want you to change the value of the neuron by the learning rate. So we will change it on 0.03, and that's a lot. I'm telling you guys it's a lot. So let's choose something smaller, like for example 0.0.0.1. Learning rate means basically that how much are we gonna learn on each step. If we reduce the learning rate, it's gonna go slower. It's gonna take longer for us in order to learn, the same things that we were learning before, but it's gonna be more stable. We're not gonna be seeing those trembles. At least we're gonna see less of them. It's gonna go slower, the learning process, I'm telling you. But that's how it's gonna go. We have chance activation on learning rate, right? Let's see how it goes now. Let's go for a play. As you can see, it's taking ages to reduce this thing. This thing was much faster before. But let's give it a try. Let's see what happens. Like, possibly we're gonna get somewhere on this. It's very likely as well that we're gonna end up on a 13 place in which we cannot go even lower. So the good part of it is you can change the parameters, you can stop the training. So I haven't stopped the training, and what I'm gonna do is I'm gonna start betting big. I'm gonna go for 0.03, and then I'm just gonna go slower. I want to learn fast as first. So let's learn fast at first. Well, the ReLU is not doing anything in here. Yeah, it's very likely it's not gonna be working for us. We need to go for something different, and I'm gonna explain you guys why. Because what's going on in here, we don't have a softmax at the end of this, right? And a softmax is something that's gonna be really helpful in order to try to classify different things, because it's gonna output us, instead of giving us a value, it's gonna give us a probability distribution. So let's go back to TAN-H, because we don't have softmax, so it's very likely we cannot do anything about it. We cannot change, as far as I can tell, each of the neurons individually. So what I could do is try to go for ReLU at the beginning and then try to go for TAN-H. That's something it's not letting us to do. So let's go with TAN-H. Alright, it's going reduce. And now that I have an idea, what I'm gonna do is, well, let's give it more time. Let's give it more time. So, yeah. Let's go TAN-H 0.03. Okay, it's gonna go lower. And not yet. When we start trembling, we're gonna reduce the right there. We start seeing trembling, so what we're gonna do is we're gonna reduce the learning rate. And we see how everything gets reduced smoothly. That happens basically because of that. Right? We see how it smooth goes. So now let's try to give it more, not that much, but a bit more, and let's see what happens. It's gonna keep learning. Yeah, it's looking nice. And at some point, I'm just gonna try to go bigger. If we go so big, it's gonna destroy the results. Look at the results right now. It's 0.231. If we go for 1, it's gonna destroy the results. It's gonna make them so unstable, as you can see. Right? So we're learning a lot of things in here. It's not good to have a high learning rate. Of course it is not. This is something good for you, but we're gonna see how fast we can reduce the thing. So we have basically ruined our training. Our training was in here, down there, and now look at how big it is. So let's try to recover the neural network. And you can play with it. You can play with the values. You can see how to improve the values and all that kind of stuff. Yeah, possibly we're gonna get into weird places, so don't do that. That's gonna ruin the different values. We can use something more. We can use regularization. Regularization is gonna help us not to learn too much the different values. So it's gonna kind of smooth this learning process quite a bit. And with regularization, it's not gonna tremble. As you can see, we have not trembled. We have not trembled. We have not trembled yet. And as we move forward, it's likely that at some point we're gonna tremble. But as you see, no, we haven't trembled at all. And this is looking more like a spiral. Yeah. We just need possibly... Yeah, it's going better, better, better with regularization. It's gonna smooth the process. So it's good to have regularization. We want to use it's very kind of, well, we're using trembling. So what we do is we reduce the learning rate quite a bit, and the trembling disappears. No more trembling. It's smooth down there. Yeah, it keeps going down. And as you can see, we are overfitting here. We are overfitting. We are learning too good that this value should be blue. There should be a continuation on this process. It's gonna be quite hard for this. It's something that you can try to see which values you can put in here. But again, look at how this orange thing looks like a spiral. This is looking as a spiral much more now. By just modifying the learning rate, giving regularization, and adding more layers, we're getting down to the thing. And it is the hardest problem of the different problems that we have right here, and I think they are organized by difficulty. Right, so we're seeing how everything is going smooth. Like, we have learned pretty much everything, and we have gone through almost 4,000 epochs. So it's gonna take a lot of time. But we are seeing these spirals now appear. If we give a lower learning rate even, we should see a more smoothing process. Right? We have seen how reducing this learning rate, we have now this thing connected that wasn't before on the blue spiral, and it's very likely that we're gonna have this spiral right here as well united. So you can see, keeps smoothing the thing, keeps going down. And we have trained the hardest model on around 5,000 epochs. That sounds great. By just modifying 3 values. So even though you don't know much about what do they do, you kind of have an idea, right? And you can have different regularization rates. It's gonna have this on a different behavior. Can we go down? Well, let's try with another problem. Let's add more layers. There's 2 ways of creating this multi-layer perception, which is basically the kind of neural network that we're testing with MLPs. We can either make this incremental, like this, 3, then 4, then 5, then 6, then 7, and then decrement them, like for example, 6, another layer. Well, we can have more than 6 layers. So there should be something like 6, and then 5, and then 4. 4, okay? We can have this kind of pyramid, okay? Or the other kind of design pattern that you're gonna find on this kind of deep learning neural networks is, well, this kind of way of doing these things, of this pyramid, was much more common in the early days. Nowadays, pretty much we have all the layers with the same amount of neurons. That's pretty much the state of the art. We don't modify them at all, right? Let's go. Let's try to train for this one. So something that you also need to know, the more layers, always the better. Not always, right? Why is that the case? Well, mainly because the more layers, the more it's gonna take the layers to learn from the previous layers. And it's very likely that in some cases you need to remove regularization, or you need to increase the learning rate, or you need to do something about it. Why? As you can see, these later neurons are not receiving pretty much any updates. Like, all the updates are happening on these first 2 layers. This is called the vanishing gradients. The vanishing gradients or spreading gradients is basically saying, hey, the neurons are not gonna receive the same kind of signals when they are trained. Like there's gonna be neurons that are gonna be more aware of the need to change the parameters than others. There's gonna be neurons at the beginning mainly that are not gonna understand, hey, how can we improve? And this is mainly happening because we have a learning rate that is pretty low. So let's increase it a bit. So in occasion it's gonna be because your learning rate is low, and in occasion it's gonna be because you have so many layers. So normally the more layers is gonna give you the better performance, but the training is gonna be harder. The lower amount of layers that you have, the less deep the neural networks are, the easier for you it's gonna be in order to learn for different features. You're gonna be able to learn these features than if you have more layers, but it's gonna be faster for these parameters to be updated. All right. So let's go. All right. Let's see. This is basically by just increasing the learning rate. You see what happened. These uses are reduced and increased, very high reduced, and all the dots are now classified correctly. It would be great to have this kind of smooth in a way, but this is basically the classification that we're doing. This is a bit harder. Let's try this one. But again, it's quite fast, right? Under 100, we have pretty much all of them classified correctly. Yeah, it's looking pretty nice. So if we don't have regularization on 80 epochs, what's gonna happen? It's gonna look more like a square. Let's see. Yeah, kind of. Possibly you couldn't see the result, but that's gonna happen. Like regularization is gonna make everything smoother, everything happening. And as you can see, these are the patterns that the neural networks are learning, and these are the weights. So for each of the inputs that you have to each neuron, there's gonna be a weight telling, hey, this input is that important. So depending on the weight for neuron X, the previous neuron is gonna be more important or less important, and the neuron is gonna pay more attention to that or less. That's how it's gonna work. Okay. And we can have regression. We can try to predict which is gonna be the more likely next value. Yeah? And we can see the loss and how everything gets classified. Yeah, this is looking nice. So this is the first introduction to neural networks. So for these kind of problems, it's more common to use ReLU, right? Yeah. But basically because we don't have a softmax. I haven't explained what a softmax is, but there's gonna be an explanation coming up soon. But yeah, you can play with it a lot. You can try different things. You can regenerate different samples of values. You can try with different of them. Like these two are quite easy. This first is easy, but the spiral is kind of harder. This process of testing with these things, this kind of that I told you before, is gonna improve how you learn. You can try to add different values of inputs and try to see how each of them improves. Like for example, if we input x1 and x2 values, or if we give just a sinusoidal of them. Let's try to add the sinusoidal. Let's see if this takes longer or not. Let's go for a tanh. Adding the sinusoidal, what I feel is gonna happen is gonna have, yeah, these regions are gonna be easier. There's a lot of trembling, we stop, we reduce the learning rate, the trembling disappears, yeah, and look at this, around 400 epochs and we have this kind of the spiral, so given the sinusoidal is improving this thing. Why? Because we are giving the data also in this kind of pattern. We're not just giving x and x1 and x2, we're also giving the sinusoidal versions of them. And that's how it works. That's how it's gonna look like. Alright, so this is for today. Hope you like it. Just go for a like, subscribe. Any questions that you may have, let me know. And see you in the next video. Bye bye.